How's it going, ladies and gentlemen? Mr. Donnie here, giving you a quick lesson on molecular polarity. How can a molecule be nonpolar if it has polar bonds? That is a thing. So hopefully what you get out of this is an understanding of what is molecular polarity and how do you tell if a molecule is polar or not. So quick review, before we can get into molecular polarity, we got to talk about bond polarity. And that all comes down to the electronegativity difference, right? That's how you tell if a bond is polar. You look at the electronegativities between the two atoms that are bonding. Are the electrons being pulled more towards one of these atoms? You compare their electronegativities, and you would see that fluorine has the highest electronegativity and carbon does not. So fluorine's going to hog those electrons, and it's going to become slightly negative, right? The electron is going to spend more time around the fluorine than it does the carbon that's being shared, which is going to make that fluorine slightly negative. Okay. So what is molecular polarity? It looks at the whole molecule instead of just a particular bond. It's looking at this whole thing. Are electrons being pulled more to one end of the molecule? With bond polarity, we were just looking at between the two atoms. With molecular polarity, we're talking about the whole molecule. Are the electrons being pulled more to one end? And you can see in this illustration that up here is more slightly negative, and then over here would be slightly positive. So this would be an example of a polar molecule. You got a negative pole and a positive pole down here. Perfect. That makes it a polar molecule. So you might be thinking, well, if it has polar bonds, wouldn't it be a polar molecule? Well, not always. Okay, so the polar bonds can be pulling the electrons in opposite directions. They'd be canceling them out. They'd be essentially a stalemated tug of war. So if we took a look at carbon dioxide for an example, the bonds are going to be polar between carbon and the oxygens. So the electrons are being pulled towards those oxygens equally because it's the same kind of bond between oxygen and carbon. So this end's going to be slightly negative, and this end's going to be slightly negative. There's no north and south pole. These things are canceling each other out. So we would get a non-polar molecule, right? They're working against each other. So I'll show you another example. Carbon tetrafluoride. So all of these bonds are going to be polar towards the fluorine. But now you got to look, okay, we got polar bonds, but look at the molecule as a whole. Look at the whole thing. All of those bonds are polar in opposite directions from each other. This bond, that polar bond is going to kind of cancel out that polar bond. This polar bond is kind of canceling out that polar bond. So overall, this would be a non-polar molecule because those polar bonds are canceling each other out. So at this point, you might be thinking, well, Mr. Donahue, how can I tell if a molecule is polar by looking at it? How can I tell? Well, first thing you're going to ask is, are there polar bonds? If not, then you have a non-polar molecule. If you don't have any polar bonds, there's no way it can be polar. Now, if there are polar bonds, the second thing you have to look at are the lines of symmetry. If there's more than one line of symmetry, it's a non-polar molecule. If it only has one or zero lines of symmetry, then you have a polar molecule. So let's take a look at some examples. Here we got HCl. Okay, do we have polar bonds? We sure do, and the polarity is pulling it towards the chlorine. Right, so we're pulling the electrons towards chlorine. Now the question is, well, how many lines of symmetry are there? Now you got to remember that these letters represent spherical atoms, right? So this is just kind of a sphere bonded to another sphere, but one's a hydrogen sphere and the other's a chlorine sphere. So how many ways can we cut this in half and give us symmetrical halves? Only one. You can only cut it in half this way, because then you would have, it'd be like cutting this in half, right? You'd have half a hydrogen on top, half a hydrogen on bottom, half a chlorine on top, and half a chlorine on bottom. That would be symmetrical. If you were to cut it in the middle, it would not be symmetrical at all. Right? You'd have a hydrogen on the left and chlorine on the right. That's not a mirror image. So because we only have one line of symmetry and a polar bond, you have a polar molecule. Take a look at another one. CH4. So there are polar bonds between the carbon and the hydrogen, and I'm actually not sure which direction they go, but they are polar bonds. But if you take a look at how many lines of symmetry you got, well, you can cut it straight down the middle. You can cut it across that way, and we could keep going, right? We have another line of symmetry. We have a bunch of lines of symmetry, so we definitely have more than one line of symmetry. which means that even though we have polar bonds, we have a non-polar molecule. And all those polar bonds are going to cancel each other out because they're in opposite directions. We got ones going that way, and we got ones going that way. It's going to cancel them out. NH3. All right, well, we have polar bonds, and I'm thinking, without looking it up because I don't have anything with me, the polarity is towards the nitrogen. So you might be thinking, well, these two polar bonds kind of cancel each other out. You're right, they kind of do. But then this third one isn't really canceled out by anything. And if you take a look, we only have one line of symmetry. We couldn't cut it in half any other way. So it has one line of symmetry. Polar bonds, which means it's a polar molecule. And I think this is the last one. Now, this one, you got to be careful not to do something silly, okay? So this is the Lewis structure for H2O. It is not this. You got to remember, go back to the other video if you need to see, well, why isn't it like this? That's wrong. Can't do that. Wrong. So this is the correct structure. So now we have polar bonds between the hydrogens and the oxygens, so that's good. It could be a polar molecule. Now, how many ways can we cut this in half and have symmetrical halves? Only one, right down the middle this way. So we have one line of symmetry and polar bonds. So we have a polar molecule. Feel free to, replay this video as many times as you need. That's all I got. I hope you found it helpful, and I'll see you in class.